Hello everyone, my name is Mr. Kim.
And I'm Ms. Silver.
Okay, so today's topic is going to be population growth patterns, and we are in an 11th, 12th grade AP biology class.
A little background on the class is you guys are taking an AP class, and half of you guys have never taken one ever before during your high school career.
Yeah, in addition to that, students in this class are highly motivated, in addition to being from a long line of high expectations.
Most of you guys are in after-school activities like clubs, sports, jobs, etc., so you guys don't have much time for homework.
Right. And the majority of class also plans on attending some of the top colleges in the nation.
Okay, so what we're going to ask you guys to do today is take out a piece of paper. This is going to act as your science journal, and as your opening activity, at the top of the page, could you guys just take a few notes as we show this video, and those notes are going to try to be the main key points that you feel have to do with population growth as you watch the video.
A 1,000 years ago, there were only 1/3 of a billion people, but we were multiplying. Now there's 7 billion of us. How did we grow so much, so fast? Say this glass is North America. The fuller the glass gets, the more people there are. Water drips in as people are born. Water drips out as people die. Okay, here's the entire world. Now let's go back 1,000 years. The Americas are nearly empty. Europe and Africa have less than 100 million people between them. And just like today, most people live in China, India, and the rest of Asia. For centuries, things stayed pretty much the same. Births are canceled out by deaths. Women are having lots of babies, but most babies die before they grow up and have families of their own. We don't reach 1 billion until 1804. But things are changing. Better medicine and better agriculture are starting to slow the leak from the bottom of the glass. People still die, of course, but more babies grow up and have babies of their own. Lots of babies. We've grown from 1 billion to 7 billion. And it only took 200 years. Will we keep going like this? Probably not. The UN says we'll level out at 10 billion by the end of the century. So as we continue to grow from 7 billion, the question is, can the world hold that many people? Experts can't agree. It all depends on how well we manage our food, water, and energy.
Okay, now that we watched the video and you guys took amazing notes, unfortunately we cannot share them, so Ed and I decided that we're going to write some notes in the video and share them with you.
So the first thing that we noticed was we wanted to concentrate all our thoughts into the US, specifically of how it increased through the movement of individuals.
Another note we made was because there was an increase in agriculture and there was an increase in medicine, the amount of births increased while the amount of deaths decreased.
Right, and another thing is experts predict that the populations will eventually stabilize somewhere along the future.
So now that we've done our anticipatory set, just a little quick overview of what our lesson objectives are as we go through our lesson.
So let's go ahead and take a look. So the first thing is we're going to be able to describe factors that affect population growth, right? The next one is going to be, we're going to distinguish between immigration and immigration, right? The next one is going to compare exponential growths to logistical growths. And the last one is we're going to explain that carrying capacity.
So as part of classroom management, how we take notes every day, I just wanted to give you guys a little refresher. So for regular vocabulary, as we go through our lesson, you'll see it in italicized words. And here's how in your science notebooks, you're going to write it as a word, you're going to provide us with a visual, and then you're going to define a word. So I just want to give you a little example. So last unit we learned about like predators and mutualism. So if I use the word predation, I'm going to write predation under word. I'm going to draw my visual, which Ed graciously provided for me, and then I'm going to write my definition and in my own words. The definition for predation is the act of killing for food. You're going to define words like this that you see in our lesson that are italicized. So that's a big...
Okay, so our next type of note-taking strategy is going to be for our dynamic vocabulary. Now it's a little bit different from our first one where we just did simple vocabulary, where we're going to just do words as well as visuals. So the first thing that we're going to do is, let me go ahead and model it for you. Our first word is going to be extinction. So first thing you do is write down extinction. And then right below it, we're going to have some associated material or something that kind of defines extinction in the context of what we're studying. So for example, let's think about the dinosaurs. Right over here, we could say that it's a meteor event, right? So we could do like meteor collision, right? And when I think about meteor collision, I'm thinking about it's going to cake the sky, there's going to be decreased light. And the last thing, if we have a decrease in light, we're going to lose a lot of our resources, right? So we're going to lose our food, so a decrease in food. And our next step is going to be our actual visual. Now, we're doing our visual, and we're gonna encounter a lot of graphs with this particular lesson. So I'm going to try to graph an extinction event. So what I think that it's going to be is, with any organism, say for instance dinosaurs, we're going to see an increase. And then as soon as that event occurs, right, our extinction event, so for example our meteor collision, we're going to see a steep decline, right? And that's what it should essentially look like. Right, and another thing is during the course of this, is when you see this, whenever you see a vocabulary word that's bolded and underlined, that is going to be part of your dynamic vocabulary.
So now that we're done reminding you guys how to take notes, let's actually start on the content. So the first question we have is, what does population growth mean? A little buzz fact that I'll probably, this last one I'll remind you, population growth is italicized, so that is one of your vocabulary words.
Right. So
population growth is basically an increase in the number of individuals of an entire population.
Okay, so we understand that population growth is dependent on the rate at which the number of individuals in a population increases in a given time. Now, this is a mathematical, ratio. So it's as the number of individuals increase and then the time stays the same, you're going to see an exponential growth.
So now, what determines population growth rate? It's actually 3 different factors. It's going to be births, deaths, and migration. Okay, so as Ed had just mentioned, he said population growth can be measured as a number. And that is true. It's actually called the population growth rate. You can actually use it as an equation. Here's actually the population growth rate equation. It's the birth rate minus the death rate equals the growth rate. Okay, let me put this into perspective for you. If we're looking at a population of deer, for instance, what would happen if the birth rate is larger than the death rate within the population? Let's look at it as an example. If there's 10 births for the deer population, and then 5 deaths occur, you get a population growth rate of 5. It's a positive number. So in general, if the birth rate is larger than the death rate, the growth rate will increase.
Okay, so Jazmine just covered what happens with an increased birth rate, but what happens when you increase the death rate? So let's go ahead and take a look. So our birth rate, let's stay the same. Let's have that at an initial 10, right? So there's 10 babies being born. But say for instance, boom, it's hunting season, right? And everyone's going to town on these deer. So our death rate starts to increase to, say for instance, 15. Right? So what ends up happening is you get a negative number, a negative 5 for our growth rate. Our population is going to start decreasing. Okay?
Okay, the last situation we're going to look at is what happens when the birth and death rates are equal. So let's keep our birth rate the same. It's going to remain at 10 again. But now, the hunters didn't get as lucky, so our death rate is going to be 10 as well. That's going to give you a nice, lovely 0. So can you say you have 0 growth rate? Not really. What we basically say is as birth and death rates are equal, the population is going to stabilize. So what happens when the birth and death rates are equal? There's no growth in the population and the population is stabilizing. So migration was one of the factors that affected population growth. What is migration exactly though? Migration is the movement of individuals into or out of a population. So for this example, this is going to be a population. Okay? There's actually two types of migration. The first one is immigration, which is the movement of individuals into a population. So these guys are actually going to move into and increase the population size. The other example or type of migration is emigration. And emigration is the movement out of a population. So as more individuals move out of a population, the population size is going to decrease.
Right now, a good example of this is actually my parents. My parents are native from Korea, and they basically decided to come to the United States in order to chase the American dream. So in the process of them moving out of Korea, they were actually emigrating out, and then as soon as they arrived into the United States, they were immigrating in.
Okay, now that we just learned about immigration and emigration, we kind of have to go back and look at our equation that we had for growth rate, where it says birth rate minus death rate equals growth rate. To modify that, you kind of have to think that, well, for birth rate, we found that that increases the growth rate, but so does immigration. As more people come in, you increase the growth rate.
Right, and we understand that death rates decrease growth rates, but so does emigration.
So now that we can modify the equation, you're going to see that birth rates plus immigration rate minus death rates plus immigration rate is going to equal your overall growth rate.
Right.
Okay, so now that we just described how population growth is affected, let's look at the mathematical models. So population growth can be described using two different models. It's going to be the exponential growth and logistical growth.
Okay, so
let's dive into those exponential and logistical growth. Buzzword, this is underlined, so this is going to be one of your dynamic vocabulary words. Exponential growth. It occurs as the population grows larger, dynamically increasing its growth rate. So as you can see depicted in this graph, it is dynamically and exponentially growing. So 2 goes to 4, 4 goes to 16, 16 goes to 32, so on and so forth. If you look here, populations grow slowly at first, as depicted in the graph, but as time passes, growth occurs more rapidly in that exponential way. The characteristic of this graph is an S-curve. So when you relate exponential growth, you're going to think, I apologize, it's a J-curve. So when you relate exponential growth to a graph, think J-curve.
Okay, so the next thing we're going to cover is something called logistical growth. Remember, it's underlined, so it's going to be part of your dynamic vocabulary, right? So the first thing that is, you can see that right over here, one of the characteristics, the other one with exponential growth was a J that you can see right here, but it tapers off, right? And when it tapers off, it kind of looks like an S, so it's known as our S-curve. So why does it exactly do this? Well, the reason why is this line that's dotted across. It's specifically a carrying capacity, right? So when populations have a carrying capacity, it is basically a minimum population size an environment can sustain. That means that, look, populations or resources are not unlimited, right? They are limited. So this is what basically happens when you either run out of food or something like that. Okay, so let's go ahead and take a deeper look into our graphs. So let's go ahead and check out this blue line. Now this blue line, it goes just like a J, and we understand that a J curve is basically indicative of an exponential growth pattern, right? So this means that it's going from 2 to 4, 4 to 16, 16 to 32, right? So we understand that they're growing really large because guess what? Resources are limitless. They have basically everything they need in order to consistently grow, right? So the next thing that we're going to look at is this red line right over here. And we can see that it basically has this S pattern. It goes from exponential, but it basically starts to taper off. And we understand that S curves are indicative of logistical growth. Now, if we take a look at this, we see that there's this line right over here. Now this line over here indicates a carrying capacity. And we understand carrying capacity is the sustainability of a population based on its resources. And something that you see right over here with logistical growth is that, over here, based on our growth rates, you have an increase of birth because great resources, right? And you have a lot of organisms coming into the population because of those resources. But right over here, as soon as you start to see it taper off, it starts to go the other way. And the growth rate is a little bit different. We start to see, based on other things like competition, limited resources, we start to see an increase in death rates. We also see an increase in emigration. We see them actually leaving the population, right?
Now that you guys have taken amazing notes on all of the vocabulary we learned today, we're going to go over how does this video, or how does the notes relate to this video that we watched at the beginning of class. So when Ed and I were taking our notes, we said human population in the U.S. has increased through the movement of individuals into the U.S.
Hey, increased, right? Now that sounds kind of familiar. Doesn't that kind of remind you of my situation with my parents?
It does.
Right?
Your parents coming, leaving, I don't remember what they did exactly, but they did change the population.
So once they came to the United States, they increased the population size.
Right.
But when they left Korea, they decreased Korea's population size.
You're right. That sounds really familiar. It sounds like immigration and immigration.
Yeah, right. So I guess my parents, when they came to the United States, they were immigrating, and when they left Korea, they were emigrating. Right?
Our second thing we wrote was, due to an increase in agriculture and medicine, more people were born and less people died.
Less people died.
Less people died.
Wow.
That was because they increased their agriculture, which is an increase in food supply, and then they increased in medicine. I mean, people lived longer, right?
Right. So everyone needed what they, in order to live longer, right?
That sounds familiar. Sounds like exponential growth.
Right.
Last one is experts predict that the population will stabilize.
Stabilize. That's interesting. So they're not growing anymore, right?
They're not.
They're not growing anymore.
So it's not exponential.
It's not.
What happens when exponential stops and we hit that like...
Right, where resources are limited.
Yeah.
Right?
That sounds like logistical growth.
Right.
And logistical growth hit that carrying capacity for the population of the United States. All right, guys, now it's your turn. We wanted to engage you in an activity virtually. So we're going to give you a series of questions, and we want you guys to make predictions at the bottom of your notes. Use your vocabulary words, your notes, any examples that we provided you to justify and explain your answers in each situation. We suggest that you draw a graph when applicable and write 1 to 2 sentences explaining each situation that we provide you with.
Okay, so let's go ahead and apply some of the concepts that we learned today. Now, right here I'm going to tell you a little bit about a marine community that scientists have been studying for the past century. Now, right over here is a representative of a kelp ecosystem along the Pacific coast. And there's 3 variables that marine scientists have been following or been basically studying, and that is CRs, as well as a kelp forest, and sea urchin. Now the reason why this is really important was because kelp forests act just like a rainforest. They house a plethora of different species, everything from nurseries to feeding grounds to just basically housing as well. So one thing that they noticed was, right over here was, along the coast there's this situation where you go underwater and there's a lot of sea urchin, right? Nothing but sea urchin, right? There's no signs of kelp, there's no signs of anything other than this particular species. And what we know that as is called an urchin barrier. So right now, go ahead and take some time, get out your notes, and explain to me exactly what does this mean as far as like dynamic vocabulary, right? What this kind of represents.
We'll give you 1 minute to answer the question. We're going to keep these pictures on the board for your reference. Again, use that dynamic vocabulary. Please write 2 or 3 sentences to explain the situation and represent what an urchin barrier would look like with growth rate patterns.
Okay, so now that you had some time to basically describe this system, go ahead and compare your notes with what I'm about to say, right? So one thing is the marine scientists basically started to figure out was that sea urchins actually eat kelp. So when they're allowed to basically feed unregulated, they start to basically show these urchin barrels, right? And we can represent that in two ways based on the material that we just covered. The first way is, right, in a graph. So right over here we have population numbers as well as over time. Now when sea urchin are allowed to basically feed unregulated, we start to see something similar to a J curve, right? And that's where we start to get that exponential growth. You know, there's a lot of kelp, they're eating a lot, in addition to that, they have, you know, all the resources they need to basically grow and multiply, right? Also known as their exponential growth. But we know that that doesn't really happen, right? We understand that kelp, it doesn't grow as fast, you know? So once our sea urchins are able to multiply like this, you know, the amount of kelp that they could eat starts to significantly decrease. So what does that mean to our urchin population, right? So what basically it starts to look like is something very similar to our S-curve, right? And we understand that our S-curve is indicative of, you know, of logistical growth. And the reason why this happens is because of something called our carrying capacity, right? And this is basically where, right? This is basically where the amount of kelp, you know, is limited.
Let's take a more look at this logistical curve. So we said the logistical curve is the S curve, and it's logistical growth. Well, when looking at logistical growth, we're not just looking at the birth rates or immigration of the population. We're also looking at the death rates and emigration. So let's look at our growth rate, population growth rate equation. You have your birth rates plus immigration minus your death rate plus emigration. Okay, and this is our growth rate. I want you guys to think of this as content, okay? We're gonna look at the S curve logistical, what's happening to the urchins. Right now the birth rate is still increasing at first, but then it's not increasing as much. So we can still put an increase. However, immigration into the population isn't occurring. As they start to eat all the kelp that's occurring. So we're going to put that as decreasing. Death rate will significantly increase as kelp decrease. They have nothing to feed on. They can't grow, the population can't increase. So we're going to increase your death rate. And then emigration. Sea urchins, despite many people's beliefs, they do move a little bit. And they will be able to leave. If they are unable to get kelp, they'll move to somewhere else. So this is also going to increase. So if you look at this in general, you have birth rate plus immigration, which I call that canceling out, minus your death rate and immigration. If you have high negative numbers, this whole entire growth rate is going to decrease.
Okay, so here's another situation. Now we understand that there's this study by marine scientists that noticed the trend. And this trend is that urchin barons significantly decreased whenever you had increased populations of sea otters, right? So then they figured out that actually sea otters eat sea urchins. So that's their relationship. So what happened in 1911 is that sea otters were almost hunted into extinction. Their pelts were really expensive and their numbers basically actually drastically declined, right? So what I want you to do right now is, based on the information that I just gave you and all the material that we covered in class, I want you to rationalize, right? What is happening to the urchin population. One more time, the urchin population. And what I want you to do is explain your reasoning or your rationale using the growth rate equation in addition to a graphical representation.
Again, we're going to give you 1 minute to fill out this information. Do not forget to justify your answer and explain as much as possible using the vocabulary you learned in today's lecture.
Okay, so let's go ahead and take a look at your answers and go ahead and compare yours with mine. Right, so the first thing is that since we have a decrease in otter population, right, sea urchin are allowed to grow, feed, multiply at their will. So what this basically starts to look like over time is that exponential growth, right? So a way to basically rationalize this is that since there's a lot more kelp growing in that area, right? Basically, urchin are eating it, they're basically multiplying, and their birth rates are increasing. So basically, giving a rationale to our growth rate, birth rates are increasing, right? Death rates are decreasing, and you have overall population growth, right? Now, the good thing about this is that if we stop this and we look at a time roughly around 1990, there was a Marine Mammal Protection Act that protected all sea otters. And what we started to see over time, right, with sea otters was an actual increase, an exponential increase in otter populations as well. So we started to see a little more of a balance later on in the 1990s. Okay, so let's go ahead and look at a third scenario. Now, during the same time, roughly around the 1990s, we understand that sea otter populations were increasing. Everything was a balanced ecosystem once again, right? But there's something that happened that was more anthropogenic, right? So the thing that basically happened was humans, right? Our need for basic resources just increased, and we started to outfish our local fisheries. Right? So we started to take the fish away. And what did that lead to? That led to local seal populations decreasing as well. Not only did they basically decrease birth rates, there's also a lot more emigration out towards the south where they could get a little bit more resources. So what happened was, we understand that killer whales, their primary food source is going to be seals, especially here in the Pacific Northwest area. Right? So what ends up happening is they have no food. So they go for the second best option. And what is that? That is going to be our little creature over here, our sea otter. But the thing, the big difference is, and the reason why this is such a big deal, is that seals and sea otters have different calories. Obviously, the seal has a lot more blubber and has a lot more calories, able to sustain a sea, an orca, right, or a killer whale. So what ends up happening was that they start eating close to around 4, even 5, in order to get the caloric intake that a single seal would provide. So what I want you to do is, using this information here, is I want you to go ahead and take a look and provide a graph and see how this basically trickles down as far as population growth, right? And I want you to use your equations and everything that we learned today and apply it, to the urchin, your otter, as well as the kelp.
Don't forget to justify your answer using the vocabulary provided in today's lecture. And we will give you 3 minutes. 2 minutes to look at these, to
Answer the question.
answer the questions.
You're tired.
Alright guys, so that just about wraps up the class. Hopefully you had enough time to write up that information. So now we're kind of going to give you a little mini assignment. What we want you guys to do is write us a paragraph, 2 paragraphs, 3 paragraphs, whatever you feel is necessary to justify what you thought these 3 graphs looked like based on the information we gave you, the lesson, and the situations. So, could you explain to, I'm sorry, we're going to only provide you with the graphs and not the any information, just so that you can double check your answers. If your graphs don't look like ours and you got it wrong, explain to us why, and then explain to us what you would have changed. Okay, so Ed, could you explain to us or draw what the urchin would look like?
Sure, so urchin populations are going to be basically unchecked. So what's going to happen is urchin populations are going to start to exponentially grow again.
The otter populations, since killer whales are feeding on them, is going to decrease. And then the kelp population, seeing as urchins feed on kelp, is also going to decrease.
Right.
Okay, we hope this information is going to help you guys out when you write it, and thank you for watching.
See you later.